board lights? The lights, these ones. Perfect. Hello, good afternoon everyone. It's our pleasure to welcome Professor Tirthankar Roy Choudhury from NCRIT IIFR, Pune for this colloquium at IMSC. Professor Roy Choudhury received his PhD from IUCAA, Pune, and after that he was a postdoctoral fellow at SISA Trieste in Italy and at the Institute of Astronomy, University of Cambridge, UK. He then joined HRI in 2008. He was there at HRI till 2012, during which time I worked on a project with him on Lyman Alpha Forest. After that he joined NCRIT IIFR and he is there till now. While Professor Roy Choudhury's works are spanned in different areas in cosmology, his major area of research is in the cosmological reionization. He has extensive works on cosmological modeling of reionization history, simulation and data analysis. Recently, he has developed a very effective semi-numerical code for reionization with photon conservation, which is also known as the script. He is the theory coordinator of the Square Kilometer Array, which is an observational effort to capture the global 21 centimeter signal, where India, especially the DAE, the Department of Atomic Energy, has recently joined. Professor Roy Choudhury will talk to us today about the tracing the first stars, insights from observation and theoretical models. So I will leave the stage for Professor Roy Choudhury.
Thank you, Dheeraj, for the kind introduction. So let me start by thanking IMSC for hosting me, and in particular Dheeraj for organizing the visit. I can use this one?
Yes, you can use it.
Yeah, So today I'm going to talk about something which excites me. This is about the first stars in our universe. The field has become extremely active because of a variety of observational efforts that have come up, and also we are expecting a lot of telescopes to be built in the near future. So just to set the stage, if you think about like the formation of structures in our universe, what do we know so far? We know that the universe was filled with tiny fluctuations, small inhomogeneities at very early times. This we know from the CMB, the cosmic microwave background observations. These observations actually capture the state of our universe when its age was about 400,000 years. In cosmology, we try to kind of measure time in a unit called redshift. Basically, that tells you by what factor the universe has expanded. So the CMB would be originating from a redshift of 1100. That means that from this 400,000 years to now, the universe has expanded by a factor which is approximately this. So we are really talking about early times. And I will use this redshift throughout my talk. So this is the state of our universe at when it was like a baby. Now, what do we also know about structures in our universe is that they are extremely rich in structures at like today, so to speak. This we know from observations of galaxy surveys. So what has been shown here is each point is a galaxy. This is a survey done, and there are various surveys which have been done. This is one typical of them. And here if you look at the distribution of galaxies, the fluctuations now are not tiny. We are not talking about 1 part in 100,000 fluctuations. They are extremely rich in structure. So you see all these voids, these filaments, and places where there are a lot of galaxies sitting. So these are probably concentration of objects here. This structure is often called the cosmic web because of the way it looks. So the question is that how did the universe evolve from a state where it was filled with very tiny fluctuations to a state where it is full of rich structures? That is essentially due to gravity. So the nature of gravity is that it is inherently unstable. So if you have even a tiny bit of fluctuations or overdensity anywhere, those places will tend to attract matter from nearby areas. So the overdense regions will grow in density and vice versa. So you will end up having all these structures you see. So the only question is, if we work this out mathematically for our universe, do they match? I mean, you treat the CMB as your initial conditions, run your equations, you have to account for the fact that the universe is expanding, so it will oppose gravity and so on. So the question is, if you put it in the equations, will things work out? Will you be able to match the observations? And indeed, they do. So that is not the point of this talk. This is just to say that we have made a lot of progress in understanding this cosmological structure formation from the epoch of CMB to today. And there are nowadays best studies using n-body simulations. So this is one such example. These simulations have become so efficient that you can now download some publicly available version of them and run on your laptop. Maybe in laptop it will be a very low resolution part, but if you have a slightly like advanced machine, you can do a lot. This is one such simulation. And what you will see is what is shown here is a redshift. So at early redshifts, when the redshifts are high, you will see that the universe looked quite homogeneous. And as the redshift decreases, time evolves, you see all these structures forming the cosmic web kind of showing up. The whole picture actually, starting from CMB to these galaxy surveys, have given rise to the so-called concordance model of cosmology, the lambda CDM model. So essentially, we think that we can describe the cosmological universe using 6 parameters. And we have measured these 6 parameters with an extremely high precision using a wide range of observations. Again, I am not going into the details here, but it has told us that the universe, what the universe is made up of, and we know that about 70% of it is dark energy, about 27% is dark matter, and only something like 4 to 5% is ordinary matter, gas and other things. Of course, this model may not be the final stories. There are a lot of unsolved issues which have crept up in recent times, and you would have heard about things like Hubble tension. We also don't understand neither the dark energy nor the dark matter, so there is a lot of things which are unanswered. Again, these are not what I am going to talk about. There are other experts. For example, Dhiraj thinks a lot about these tensions and so on, so you should talk to him if you know about these things. I am going to talk about a phase which is relatively unexplored. So we will just go ahead and see what I am going to talk about now. So again, just to summarize the story, we know that when the universe was 400,000 years, we had these small fluctuations. This we know from CMB. We also know that when the universe is what it is today, we see all these galaxies and the large scale structure, and we think that this is all because of gravitational instability. The observations of galaxy surveys are kind of pushing the boundary, and we have reached a stage where we can observe galaxies up to redshifts of 6 and somewhat beyond, and I will come to more precise numbers very soon. So the thing is, this is the part we have observed. Like, we have data to see how the universe looks like. We have data from this part, and we know how the universe looked like at these early times. However, there is still this area, there is this gray zone, where we do not have direct observational evidence of what the universe looked like. And this part is also very interesting, because as you can understand that you had all these small fluctuations, then they grew into these galaxies. So there will be a time when the first galaxies or the first stars in our universe form. It has to be between the CMB and where we are observing the galaxies so far, but we really don't know when exactly. We also don't know how these first galaxies look like, whether they are similar to the galaxies we see around us, and so on. So this has become a very important field of study. Lot of observational effort, as I was saying earlier, is being spent to kind of go and find signatures of the universe at this stage. There is no direct. Indirect ones will be, for example, again, I'm think about reionization. Tau, for example. So all the CMB photons have traveled through this part and they carry some signature. It's just that we don't know what exactly happened here. And similarly, Lyman alpha forest and things like that. But we don't have a signal exactly originating from that redshift. Yeah. In the CMB is integrated effect, and anything, you can also say that I have a theoretical model where you start from here and it goes up to this part. So we think we understand what is going on. But they are still indirect in that sense. Yeah. I will have like 1/3 of a slide on that. Yeah. Yes, but that's part of what I'm going to talk about. Yeah. So this is where we are now, and this is going to be the focus of my talk. Again, just to give you some idea, I'm going to talk about the universe when its age was something like 100 million years to 1 billion years. And the corresponding redshifts would have been something like 15, 20 to about 6, 5 or something like that. As I said, most of the time I will be talking in terms of redshifts, but if you want to convert that into like age of the universe, you can use some of these numbers. So that is something to keep in mind. Yeah. Very unlikely. What we understand about dark energy is that it became dominant very late, and we are talking about redshifts of 1 or so. Unless you need a very exotic model of dark energy to solve some of the tensions I mentioned. But that is an open question. If we think about lambda CDM, the concordance cosmological model, dark energy is extremely recent phenomenon. So yeah, here it will be, it's almost like what we call Einstein de Sitter universe. It's dominated by non-relativistic matter, which is mostly dark matter. Yes. No, I will come to that. So this is where JWST is. So if you ask me the question today, it will be some answer. Next week the answer may change. So field is moving such a way, and I will show you some results. Yeah, there. Just to set again the tone of what I am going to talk about is the formation of these first stars and galaxies, and what we understand broadly is this. As the universe was expanding, all these small inhomogeneities were growing, so structures were forming, and regions which have high density will eventually kind of decouple from the expansion of the universe, will turn over and collapse. Okay? They will collapse and form something which we call dark matter halo. So this dark matter halo will form a stable structure where the gravity will be balanced by some random motions of the particles which it's made up of. And this dark matter halo will then kind of attract the normal matter, which is of course less in amount. And this normal matter then what we call falls into these dark matter halos. They will then cool and condense, and all sorts of astrophysical processes have to take place from them to form stars. So this is how stars form in our universe. What we also understand is structure formation is hierarchical. That means small dark matter halos form first, then they merge and form large halos. So the initial halos would be like small. So we also expect the initial galaxies to be kind of smaller than the galaxies we see around us today. So why do we say still expect down some of the hierarchical, as far as dark matter is concerned, hierarchical structure formation is clear. The uncertainty will arise only because of the gas physics. So it is not clear. So if you have too small a halo, it is not very easy to cool the gas there. You need a halo of certain size and above for it to cool. What will happen is, so the gas, let us say it has settled down, it will pick up the temperature corresponding to the virial temperature of the halo. Now, if it is, let us say something like 1000 Kelvin, what will happen is the gas will be mostly neutral. Think of hydrogen, it's neutral, and it will have no way to cool. It will just remain. However, if you go to a higher, larger halo, which has a temperature of 10 to the 4 Kelvin and above, there the hydrogen can get ionized or at least excited. because of collisions and whatever, if it gets excited, it will come down and the radiation can take the energy out. So that is how you have to cool. So you need a hot gas to cool it, basically. So it's that. So now you can go into more details and ask whether, whether even these small halos cool, or do you need more favorable conditions and things like that. But generally, as far as our theoretical understanding goes, that galaxies kind of follow these hierarchical structures. Okay, but yeah, we don't know. We have to see what happens with observations. And then there are other effects. If you form stars, that doesn't mean it will keep on forming stars. The stars can kind of throw energy, and that can kind of, for example, heat up or expel the gas and can prohibit the next generation of star formation and so on. So we broadly understand this part, but the details are not clear, particularly related to this cooling of gas, these feedback processes and so on. And that is where lot of research is going on. This is where observations can also help. Now suppose you want to go and detect these first stars observationally. So what will you do? You will basically make more and more sensitive telescopes, because these stars, the light is coming from far away, and so they will become fainter essentially. Apparently they will become fainter, their flux will be less. So you need to make more and more sensitive telescopes, and they should be in particular wavelength range so that they will be observable. And this is where the recently launched James Webb Space Telescope is kind of breaking records. So this is one plot which captures that. This plot is also almost a couple of years old, and this has changed quite a bit, but the basic point still remains. What has been shown here is the luminosity of the galaxies versus redshift. You can also see the age of the universe in this in the upper axis. Before JWST came, we had these blue points from HST, basically Hubble Space Telescope. They were fewer in number. The redshift range they covered was mostly confined to redshifts below 8 or so. We had only a few above that. And the luminosities were high. We were looking at only the bright galaxies at that stage. Now once JWST came, so these are all these orange points, you can see the landscape change completely. Firstly, we are now detecting a lot of faint galaxies which we did not have any idea about before JWST went up. And we are pushing the redshift frontier. And now we have detected galaxies to redshifts as high as kind of 15 or so. So this is the kind of redshifts we are talking about. There are candidates which have higher redshifts, but they haven't been confirmed yet spectroscopically. So their redshifts haven't been confirmed yet. So that's so this is the kind of redshifts where we are at present. I mean, again, this is because we were interested in reionization and things like that. Roughly there, yes. So this plot was made just to make the point that how the redshift barrier is being breached, and yeah. So 6 is just a typical number. There is nothing special about it, yeah. Sorry, yeah.
What are they detecting here? Are they detecting X-rays from
No.
galaxies?
They are detecting galaxies at rest frame UV optical. When they reach us, they have probably shifted to near infrared or something like that. So they are basically detecting, okay, so different galaxies are detected using different techniques, but they are basically detecting some kind of an emission line arising from atomic transitions within the galaxy. Okay, it could be oxygen, it could be hydrogen or something, some emission which is happening inside the galaxy. Okay. But not X-rays, no. So these are UV optical. That is the baryonic whatever, yeah. Yes, exactly. Not dark matter. Dark matter won't form stars, obviously, yes. So normal matter will give rise to stars. Yeah.
If I look at the highest redshift
yes.
one, so the reason why it is so bright is because it's very big, or what I mean, it's very luminous. Even
it is luminous, obviously, it's high luminosity.
And why is that?
I mean, it's probably purely a selection effect. So the first galaxies we will detect at any given redshift are likely to be the intrinsically brighter ones. They are easier to detect. It's possibly, if we had a telescope which could see all the galaxies, probably this part would also have been filled up. We don't know, of course.
So this is intrinsic luminosity then?
This is intrinsic. What has been plotted here is the intrinsic luminosity in some very complicated unit which the observer used called magnitude. Yeah. It's the intrinsic luminosity, not the flux measured. No. Its field of view is very small and different. So there are different surveys going on, and different surveys actually scan different parts of the sky. Yes. It depends on what the proposal. I mean, these are basically proposal-driven surveys. So they are. Many of the surveys are actually looking at sky which has been like extensively observed by others, like HST or other wave band telescopes. But there are new fields as well. Now, if you go and now, for example, do some quantitative study, one thing what people does is something called luminosity function. So this is what has been plotted here. The x-axis is the luminosity, but remember luminosity increases this way, and this is the number of galaxies in that luminosity bin. This is purely observational. These are for different redshifts. The point is not to go into too much details about this plot. But what I want to emphasize is that you can see the number of galaxies are increasing at lower luminosity. So actually the universe is filled with fainter and fainter galaxies, and we don't know where this curve is going to turn over. We don't know observationally. If you have a theoretical model, you will know, but observationally we haven't seen this turnover happening. So it is possible that the galaxies we have observed so far are not even representative. You are only observing a very few bright galaxies which are easier to observe, and the representative population is completely different. So now there still remains a question about how do we then understand the state of the universe where the representative set of galaxies are very different from what we have observed so far. And this is where we need complementary observations, complementary ways to observe the universe at these redshifts. And this is where hydrogen plays a role. And that takes me to my next point, which is to do with reionization, which Dhiraj also mentioned. Reionization of hydrogen by first star. So I will illustrate it through a cartoon, and then we will come to more quantitative and more rigorous discussions. So imagine the universe filled up with hydrogen, and some signal from that hydrogen is coming to us. Okay, so this is basically hydrogen atom. Now at some point you form the first stars or a galaxy here. That galaxy will emit radiation, and that radiation will have photons above the ionization threshold of hydrogen, let's say 13.6 electron volts. So what it will do is it will ionize the hydrogen around that. So you are receiving signal from here, but you will stop receiving signal if you form a star somewhere in the vicinity of the hydrogen atom. So then what will happen to this hydrogen atom? Since this hydrogen is far away from that star, probably it will still survive because the radiation may not have reached that point. So what will happen is soon you will find that the universe is kind of separated into two phases. One phase which are near where the galaxies have formed, and there you don't see signal from neutral hydrogen because hydrogen atoms have been dissociated. And far away from the galaxies, you will find hydrogen atoms still remaining. This phenomena now will be kind of dominated by whatever galaxies dominate the population at this stage. So this process is not kind of biased towards these bright galaxies. So if you have a large number of faint galaxies, they will drive this reionization. So this process is called reionization because you are ionizing the hydrogen again, so to speak. So for example, our sun may not be emitting hydrogen ionizing photons very easily. So it depends. I mean, think of them a black body kind of a thing. So our sun doesn't have that much energy. So you need these very heavy so-called OB stars. They are the kind of producers of hydrogen ionizing photons. So I mean even our galaxy will have such stars. They may not be typical, but these massive stars kind of occur and they ionize.
Unless heavier galaxies are unlikely to have more stars or something like that, they will all ionize equally still, right?
No, that will now depend on the model, right? I mean, so fainter galaxies, okay, so a faint galaxies will probably produce less ionizing photons compared to a bright galaxy, but they are more in number. So now it's a question of which one wins. Okay? But whatever it is, this process does not distinguish between faint and large galaxies, and yeah. So typically what happens for most models, it's basically the faint galaxies which will dominate, unless there is a process which will. In principle, yes, but we are still not there yet. Yes. Because, or at least for reionization, we would like to study the heaviest stars, basically. But then if you are modeling star formation in a galaxy, you cannot simply model only the heavier stars, because you have to model everything. And as I said, we are not there yet, at least theoretically. Yeah. Yes. No, this is a cartoon, so this is more like a proper simulation. So this is, for example, the universe, the matter in our universe, which is growing. The fluctuations are growing, and these are places where galaxies will form. They are the densest structures. Now this is the matter part. This is neutral hydrogen. So red one is neutral hydrogen. The black is kind of ionized. So what you will see is wherever you are forming these galaxies, you will form these bubbles around that. And then soon these bubbles will merge with bubbles coming from nearby galaxies. They will grow. So there is a percolation which is happening and eventually ionizing the universe. This of course is a simulation. We haven't observed this yet, but this is some model which matches the existing observation. So we think that this is the process. This is, yeah. What happens is, as opposed to Stromgren spheres in ISM, where you actually come to a stage where recombination is kind of balancing ionization, such a thing does not happen in the low density intergalactic medium. They keep on growing. But the basic physics is exactly like Stromgren sphere, except you don't have this equilibrium radius kind of a thing. Yeah. Okay.
Since there are free protons,
Yes.
and they are moving about, don't they generate magnetic fields which can also further influence?
Yeah, they are extremely non-relativistic. The kind of temperatures we are talking about, they're very unlikely to generate any real electromagnetic signature.
Is it fair to say there are no primordial magnetic fields?
No, there could be. It's just that these ones won't be affecting that magnetic field. Their trajectories, particularly electrons, their trajectories may be affected by the existing magnetic field, but they're not going to generate anything new.
Did that go into these simulations?
No. These simulations don't take into account, particularly because we don't know much about them. Yeah. And also in the intergalactic medium, we understand that the magnetic field is extremely weak, so they are unlikely to affect the conclusions we are drawing here. The magnetic field can have lot of influence in the star formation itself, which we anyway don't understand. All these processes which I wrote, cooling and other things. Yeah.
So are you?
Yeah. At lower redshift. 10, 16. Yes, and this could be, Gauss, exactly.
So are you saying that the neutral hydrogen signal from the universe is actually very weak today?
Yes, so we are living in a completely ionized universe. So all the neutral hydrogen in our universe are confined to within these galaxies. These galaxies resist this ionizing radiation because they have high density. So even if you ionize, they will recombine very fast. The densities are higher. The bulk of the universe is completely ionized. And this we know from observation. So we are living in a plasma, basically. Yeah. So the universe started with a plasma, it became neutral for about, I don't know, 100 million to 1 billion years it remained mostly neutral, and then it got ionized again. So, and this part we know very well from different observations, except details are still unclear. Yeah.
So maybe it's a naive question, but why are these photons never detected? Do they don't?
Which photons are never detected?
The photons which ionize the hydrogen.
Because they are absorbed when they are ionizing. And it's good that we are not detecting them.
Okay.
We detect them from lower redshifts when the universe is completely ionized. So we detect the ionizing background. Yes.
Okay. And
there we do.
Can it be some other particle besides photons and neutrinos or something like that which
Yes.
can do the reionization?
In principle, yes. We think that if the galaxies have formed, they are likely to ionize the universe. But suppose there is some process which is stopping galaxies from ionizing the universe. One good example is, suppose there is enough hydrogen within the galaxy and all the ionizing photons get trapped inside the galaxy and they are not coming out. They are not so-called escaping. Then this picture won't hold. And since we know that reionization has happened, then you have to go for some more exotic sources. People have studied things like annihilating dark matter and things like that, but there are strong constraints on them from X-rays and other things. So it's not very easy to do without galaxies, but unless we have a definite answer, some of these possibilities do remain open.
And maybe I missed this, but how do you know that reionization has happened in the universe?
I think it's next slide. I will come to that. Yeah.
We can keep track here of the fraction of reionization, I guess, right?
Fraction of hydrogen that is ionized, kind of a thing.
Yes,
You are talking about that.
Yeah, so if we go from the red, which is unionized,
Yes.
to the black, which is, I suppose, fully ionized? Or
Yes. Black is fully ionized, yes.
Or a small fraction of...
No, it's fully ionized.
Is it 100%?
Yes, so what happens is, the optical depth or the mean free path of ionizing photons, even in a very mildly neutral medium, is extremely small. So unless they completely ionize, and when I say completely ionize, I am talking about 1 part in 1,000 to 1 part in 100,000. So it's extremely small.
Okay.
So that remains because there will always be some residual recombinations happening. So that you cannot stop. So the black regions would be ionized to the level of 1 part in 1,000 or less.
So then,
neutral.
as the fraction of reionization or ionization changes,
Yes.
the signal also will gradually fail, I guess, as a function
Yes.
of
So any signal you are expecting from neutral hydrogen
Yeah.
will actually decrease and eventually go to zero as you come here.
and as a function of redshift, in principle, it is observable.
It is, and I don't know if I will have time to go into that, and that is the future observations are targeting exactly this. Yeah, no, please.
You said 1 in 1,000, 1 in 100,000.
Yes.
Does it? Thanks. Does it mean ionized or the fraction that is not ionized?
Neutral.
Ah,
So 1 part in 1,000 is neutral.
So it's like 99.99% ionized.
Ionized in these black regions.
Thanks.
And the red regions are completely neutral because the radiation hasn't reached there. Once this is all black here, that means the whole universe is probably 1 part in 1,000 neutral. Or 1 part in 100,000 neutral, depends on how much radiation you have produced. Yes. And the importance of reionization is immense. So as you can understand, it gives you a complementary way to study the fast galaxies, complementary to direct detection. So it will tell us a lot about the astrophysics during that time. It also tells a lot about cosmology because the underlying matter field and the formation of these structures is dominated by the cosmological field.
Sorry.
Now coming to observational
Sorry,
probes.
what do you mean by first galaxies?
So at some point you will form. So at very early universe there were no luminous sources.
Luminous.
Yes,
So first stars make sense to me, but first galaxy is equated to first stars?
roughly yes, because as far as we know, stars are forming inside galaxies in these halos where galaxies form and so on.
Okay.
So I have been using this interchangeably. Yeah.
And do n-body simulations tell you at what Z that is supposed to
No. So n-body simulations are very good when you run gravity-only simulation. Now, gravity-only simulation is basically dark matter simulation. Now, tracing the gas physics is extremely challenging there. If you want to trace the formation of stars, you have to go to very small length scales, then you have to give up on the cosmology part, and vice versa. So no. So that is the part we are still missing theoretically, and we need some observational anchor to help us in understanding what is going on. And that is why JWST and all these observations will help, basically. So this match needs to happen.
Do you have any expectation on what the first stars should be?
Okay. As of now, I don't have an answer. What happened was 3 years back, experiment called EDGES, and I haven't gone into what signal they were detecting. They gave some indication when the first stars formed, and they were talking about redshifts of 18 to 20. However, that result has been kind of retracted. Some other observations could not find that signal, so it is not clear whether that signal exists or not. But that is the typical redshifts. And as you would have seen, JWST has anyway detected something up to redshift 15. So now the gap is kind of shrinking, but it will depend now. I mean, if the future observations show that it is redshift 20 or 25, it may. I mean, there's nothing which stops it. But yeah, we don't have a number. They haven't officially retracted, that is true. I should have been more careful. But they haven't responded to the criticism. The criticism came 2 years back and there were no response to that. So the community thinks that they don't have anything to say at this stage. So we don't trust that result anymore. So the observational probes of reionization are many. So basically, one way of probing is through Lyman alpha absorption. So what happens is you have a very bright source in the universe at very early high redshift. The light is coming from that source to us, and in between, if there is neutral hydrogen sitting, there will be absorption of that light because of Lyman alpha transition. And that will show up as an absorption signature in the spectra of this source. And these sources have to be very bright to detect this signal, and these are typically what we call quasars. Now what they show, this quasar spectra, I mean, if you concentrate on this part of the spectra, so what has been plotted here is some flux in some arbitrary units versus wavelength. You will see all these absorption signatures. These absorption signatures are arising because of Lyman alpha transition, and hence this part of the spectra is known as Lyman alpha forest. What you can do is you can model or calculate the amount of hydrogen needed to produce these absorption signatures. And if you stick to something like redshift 5 and below, these observations will tell you that you cannot have neutral hydrogen fraction more than 1 part in 1000 or 10,000 or 100,000. It will be more like 1 part in 1000 here, and it is definitely less than 1 part in 100,000 at these epochs. Okay, this is how we know that the universe got reionized. Okay, there is no way you can escape that. If the neutral hydrogen fraction was slightly higher, what would have happened is everything here would have been absorbed. So you would have seen complete darkness here. It would be consistent with 0. 6 point, yeah, roughly there, exactly. So this is, now you see whatever I was talking about is showing up at redshift 6.3. If you do a naive calculation, it will only tell you that the neutral hydrogen fraction is greater than 1 part in 1000. So Lyman alpha transition is so strong that even 1 in 1000 atom will produce something which looks like this. Of course, you can learn a bit more if you now have to go and model these spikes and all these things. So that is a separate question. But now, so this is what tells us that the universe must have been ionized at some redshift between these. Okay? So this is how we know.
Sorry, very basic question. So,
Yeah.
like, it should always be lines, right? So, like, how come, at 6.29 it's completely...
Okay. So what happens is, as I said, imagine that the universe is greater than 1 part in 1000 neutral. that is enough to absorb all the light. So the number of absorptions happening, or what we call the optical depth, is so high that it will kind of absorb all the light here and it will go to 0. Okay. So other way, what you will see is these lines will start to come closer and closer, and what we call blend, and will slowly go to 0.
So why would they come closer?
Because, okay. So now let us take a step back. You are seeing an absorption here, but suppose you are not seeing an absorption here. What does that mean? Probably this one has a slightly higher density and this one is ionized to 1 part in 10 to the 5. Okay. So that is why you are not seeing much absorption here. Now suppose I make this 1 part in 10 to the 5 to 1 part in 1000 or more, the neutral fraction. This thing will just go down here.
Sorry, this is frequency, is it?
This is where, wavelength of frequency.
Yeah.
Exactly. So the whole thing will just go down if I make the neutral hydrogen higher and higher.
Maybe I'll talk to you later.
Yeah. But this is basically it. The other observational evidence comes from CMB. So what's happening is CMB photons are traveling from this what we call last scattering surface to us. They are free streaming through this neutral universe. But the moment now you ionize our universe, it is producing, of course the protons are there, but it is also producing free electrons. And the CMB photons start scattering, basically Thomson scattering of these free electrons. And this gives rise to various secondary signatures in the CMB. And one of them has to do with polarization at low L, something, it also damps the temperature anisotropies, detecting them is a problem. So there is a lot of story here. But what I'm trying to say is CMB also captures information about reionization. And you will realize that these two probes are also complementary to each other in the sense this one probes the neutral component and this one probes the ionized component. Of course, this one is arising from a line transition, so you can do redshift by redshift. This one is a integrated effect. Okay? So it's sometimes more difficult to interpret these results. In the plot, okay. So what I have plotted here is the anisotropy. So this is the temperature anisotropy. This is the polarization, okay. It's actually TE cross power spectrum. This point is arising from reionization, low L high signal. But as I'm saying, this is not the only signal. There are other signatures hidden here, which are difficult, but this is very prominent in that sense. And there are other signatures also, but I'm not going to that because they are relatively indirect. But the future is 21 centimeter emission from neutral hydrogen. Now here, because 21 centimeter emission is weak, it's a forbidden transition, it's not like strong as Lyman alpha. What you can do is, even when the universe is reasonably neutral, you will get signal. What happens is Lyman alpha just saturates, it doesn't give you any signal at these stages. So this is the experiment which we are hoping to use to actually map out the picture which I talked about. This redshift by redshift, what is the neutral hydrogen fraction, okay, in the universe. But we haven't observed this signal, and that is to do with what's happening in the future. So these are basically the different hyperfine states of the ground state of the neutral hydrogen. So once you make this transition, it will go from one state to the other. This is happening because of the interaction between the electron and the proton spin, basically. Okay, so you will form these triplet and singlet states and so on. So one will be higher, one will be lower, and you can calculate the difference between them will be 21 centimeter in wavelength in the rest frame. Of course, we will observe it at a higher wavelength because of redshift, but this is a very strong probe of neutral hydrogen in astrophysics. So we have observed this signal from nearby galaxies, and it's being used a lot for doing lot of science, but we haven't observed the cosmological signal at high redshift yet because it's very weak. Yeah. Yes, but the point, the saturation point will become clear here. So you pointed out that this is like almost consistent with 0. And I told you that it will become 0 the moment the neutral hydrogen fraction becomes 1 part in 10 to the 3. it will remain 0 if the neutral hydrogen fraction is 1 also. Now you cannot distinguish between 1 part in 10 to the 3 and 1 because it is absorbing all the photons anyway. Okay, so it's becoming insensitive to the reionization process. I want to understand how the universe went from like 0 ionized to 1 ionized, and it is becoming completely insensitive beyond some point. So Lyman alpha is very good in probing the ionized universe and probably late stages of reionization when it's ending, but then it becomes completely useless. And this is where 21 centimeter will play a big role. CMB of course has signal from reionization, but it is integrated. So 21 centimeter has this very nice properties.
Sorry.
Yeah.
Is there a dipole-dipole interaction between the atoms, or is that not relevant?
Come again, sorry?
So, between two hydrogen atoms, is there a dipole interaction?
No, there is no. We are talking about the electron and the proton interaction.
Ah, here fine, but I am asking a different question. Is there a dipole interaction possible?
I mean, even if it is possible, I mean, we are talking about really low densities.
So that's not relevant. Okay. No.
Too small. Even in like galaxies, it's not there. And this is we are really. So yeah. So again, just to summarize this part, so this is where I mean reionization and these first galaxies have become so interesting. We are talking about a wide variety of observations over a wide redshift range. We are starting with quasar absorption spectra and high redshift galaxies, which are kind of in the rest frame mostly UV optical, to CMB anisotropies, which is microwave, to 21 centimeter, which is actually happening at radio wavelength. So all these observations are probing different kind of facets of this early universe reionization cosmology, and every all these different kind of probes have, I mean, there is already ongoing experiments and there are plans to set new experiments in the near future. The physics of reionization is quite detailed. I mean, as I already have hinted, you have to worry about dark matter halos, how stars form within these dark matter halos, what kind of spectra they produce. If you have a model for this, you will be able to predict the galaxy luminosity function. And this is something we have been doing for quite some time. So this is a result from what we have done very recently. What has been plotted here are observations of the luminosity function coming from existing, pre-JWST observations like HST and also JWST. All these high redshift points are from JWST, and this is like some model we made. I am not going into the details, and once we match the observations, that free parameters of that model got fixed, and this is how it compares with the observations. But what happens is we are not only comparing with this luminosity function, we are actually then trying to see what happens to various other observations like the clustering of galaxies, the reionization history itself. This is something called inverse of star formation time scale. This is the name, the technical name is specific star formation rate, and so on. But what I'm saying is JWST, what has happened is it has enabled a wide variety of kind of observables to be calculated, and now you have to make theoretical models which are kind of consistent with a wide range of observations. The error bars are still large because at high redshift the number of galaxies we have detected is not very high, so these will become more precise with more and more galaxies being observed. There could also be question about systematics because people are in a hurry to analyze this data and publish, and often we have seen these points getting revised. And for example, this paper from where we took the data, the first version in the archive had a different set of points, and we had already almost written the paper, and then we realized that they have revised the paper where the points have changed. They found some systematics in the data, so they had to redo the analysis again. And I mean, things are moving so fast. Even today there is a paper which gives new points here. So now we have to go back and check whether our model matches those points or not. So the field is really active, and this is big driven. JWST galaxies, and you are basically measuring the measure the clustering. And what I have plotted here is something called galaxy bias. You are just dividing by the dark matter power spectrum or correlation function at large scales. And then you can predict from the theory. If you know how to populate galaxies in dark matter halos, you will be able to calculate the clustering analytically, and then you match this. Yeah. So clustering, they will measure clustering as a function of angle in the sky. But what has been plotted here is basically the large scale clustering, because there we expect the clustering to be proportional to the underlying dark matter power spectrum with the bias term, which is almost scale free at that stage. So this is the galaxy bias. So we are basically computing the large scale clustering. Small scale clustering is slightly difficult to compute, particularly in the kind of analytical models we are working about, because there you have to take some nonlinearities into account. Large scale clustering is relatively easier to compute. They will go to few arc seconds basically. So it will go to few megaparsecs, to tens of megaparsecs, co-moving. Roughly, I'm giving you very rough numbers. Yeah. But we are hopefully in that scale-free bias regime by that time. At least the largest scales they are probing. Yes. And we are nowhere close. So.
I understand. So what am I looking for? I mean, what should I be? What are the parameters you are,
Yes.
will the concordance model be described by?
Yes.
What are the functions?
So we, as of now, we don't know how many parameters we will need to describe the concordance model. That is very clear. But what we want to know, at least zeroth order, the first thing we want to know is the what we call the amount of hydrogen that is ionized globally as a function of redshift. That is this plot. Okay. Again, you may think that there are measurements, but these measurements are extremely model dependent. I have plotted it just to show that roughly the models match what other people find. But this curve is what we are looking for at the first go.
But that curve is not surprising.
That curve, what we are getting at present, this story is probably.
In other words, when you have some model which will predict a function of redshift.
Meaning?
That quantity.
Yes.
That curve.
Yes.
You're drawn.
Yes.
I mean, do you have a simpler model that will fit as a function of redshift?
You can have a simpler model that will.
Simple toy model.
Yes.
Picture.
Yes.
And that is, you're looking at deviations from and so on.
Yes. No. Okay. So let us take a step back. So when I say what we are looking for is a observational measurement of this quantity as a function of redshift. Now, when you model, of course, now it depends on what you are trying to do. Suppose you want to predict the CMB signal. That basically depends on this integrated quantity. There you can just say, put a parameterized form and do that. But now suppose I want to take the next step, that given this curve, I want to understand the properties of the first galaxies. Okay, when did they form, how did they look like? Now I have to go into more detailed modeling, and I will hint upon that if I have time. So Dhiraj, what is the time now? Okay, you have enough. Okay, fine.
There are discussions we can do.
Fine, you let me know. Yes. Yes.
These are observations, the right plot, the right top. Yeah, that.
These ones.
Yeah.
Okay, so just to be sure, these are really observations coming
Okay.
from observations. These points are also coming from observations. These are basically, this is a combination of observation and some theoretical modeling, which gives rise to these points with error bars. So there will be some observations, maybe related to laminar alpha absorption or something, some galaxy showing some property. Then they will model and find out what kind of neutral hydrogen fraction they need to match that observation. So this is not strictly speaking an observational data point. So the information about that model has gone into these data
So
points.
the error bars is some characterization of the model uncertainty, or
Yes,
is it not?
yeah, both. I mean, so it
Okay.
has the characterization of the model uncertainty and also the uncertainty in that observable which they were.
But still, you would not think of this as actually observing the.
No,
Why
because
is that? Yeah.
because it depends on that model they have used, that simulation they have used, and I may or may not trust that
But that-
simulation.
Uncertainty is included in the error bar, no?
Yes. Now we are going into more details.
Okay,
now I
maybe
can
we can
ask.
talk later.
No, but
Yeah.
what you have pointed out is correct. I may say that the simulation they have run doesn't account for all the theoretical uncertainties that can go into the.
Okay.
So there it becomes a bit subjective.
Yeah.
But yes, so that is why
Okay.
I don't put these points at the same status as these. These are direct observations, something I'm getting from the sky.
Okay.
There some prejudice of whoever wrote that paper has gone in. So strictly speaking, if I want to take these observations into account, I should run my model and predict those observables which they have used to get this point. We will do that eventually, but that takes a bit of more work. So
Is this all JWST data? Or
no.
It's
So
all-
these two are JWST
No, that
data.
one, yeah.
Here, they come from different. Okay, because some of them are quasar absorption measurements. These ones, so they are anyway not JWST. Yeah. But these two are extremely JWST driven. These kind of data we did not have, let's say, even a couple of years back. Yeah.
Is there any relation between the effective galaxy bias and that neutral hydrogen fraction? If you
What do you mean relation? No.
There is any dependency.
No. You can have models. You can have two models which have very different clustering properties, but give the same globally average neutral fraction. You can. So yeah. But those two models, reionization will be driven by very different kind of galaxies. Basically. And now you can go and ask that what does this model imply given that it matches observation, and there are various things. We think that star formation was extremely efficient at high redshifts because that's what the model needs. The nature of star formation was very bursty, so the galaxies will form like stars in some 50 to 100 million years, and then they will exhaust all the fuel, and then they will stop. Again, I don't have a very physical model of how this is happening, but in principle, this is what the model kind of demands. So just to give you an idea about where we are heading with our understanding of galaxy formation at early times.
Is that star formation rate or what?
This one?
Yeah.
This one is so this one is the time scale of star formation, and this one is the amount of gas that goes into stars. See, not all the gas in the galaxy will go into stars. We know, in our galaxy there are stars and there is this interstellar medium. So this is that fraction. What JWST has been telling us is that you need galaxies to be brighter than what we expected from low redshift observations. Now, you can make the galaxies brighter in two ways. You can say that I will put more gas into stars, or I will form stars in a less amount of time. So that will make things brighter. Luminosity has a per time. So this is what. But now, if you take only one set of observations, like this, you may not be able to break this degeneracy. And this is where all these other observations help. Now you can say which one should increase, which one should decrease, and so on.
So if T star increases, then we have lower number of stars formed, is that right?
No, stars are forming in a very small amount of time. So what will happen is
T
T
star
star.
increases means stars are forming at larger time. No?
Increasing means it is forming,
Taking longer to form.
take it longer to form. Yes, that is
So
correct.
you would expect lower number of stars to be formed.
No, it could be more, the number of stars could be same, but they are forming, so these two could be, in principle, independent. When you actually make a physical model, probably they will get related, but we are, as I said, we are not at that stage.
And at lower redshifts, you have a higher over density, right? Because the density is still growing.
Density is growing.
And
Yes.
so you would expect more stars to be formed at lower redshifts?
In principle, yes,
Okay.
that is true. Its star formation should be easier at lower redshift. Yes.
Then you can interpret that the fact that it is coming down at large redshift implies more star formation.
This quicker star formation. More star formation would be more related to this. How much amount of matter is going into stars?
Power somewhere in addition to the rate of formation.
Yes. Yeah.
That part is a forbidden region.
No, this is the part where we have data. Okay, so you will see the model is becoming wider and wider because we don't have many data at these redshifts. So the model answered. So there are a lot of models which are kind of consistent with the data. So these curves show you all the models that are kind of consistent with the data. And that is tighter at lower redshift and it is becoming broader at higher redshift. These 2 points tell you where the clustering measurements are, and these shaded regions tell you the luminosity function measurements we have used. Yeah. Again, I mean, as I said, newer and newer papers are coming and we don't know. These models will get revised very soon or maybe ruled out and we don't know. So it's really, we have to look at almost day-to-day basis. Okay. Yeah. Yes. So our model won't tell you why is it happening. It will tell you you need it to increase to match the data. But there is literature. What people think is here, okay, there could be many things. One is happening, the way to look at it is the composition of the universe is very different at these redshifts compared to this. Why is that? Because the initial gas is mostly made up of hydrogen and helium. That is what the universe is made up of. You make more stars, they will basically start so-called polluting the environment. So you will have what we call metals. In astrophysics, anything higher than helium is metal. So it will filled up with, who knows, I mean, oxygen and carbon and other things. So the next generation of stars are forming in a very different environment. So that can qualitatively explain this. Whether quantitatively we can explain it is a different question. Now we have to run a full model to see whether the amount of these metals produced is consistent with the amount of decrease we need.
If you have more pollution, the rate goes down. It is more difficult to form.
No, what happens is, so it's slightly tricky. What happens is, in some sense, cooling becomes easier because you have access to more transitions. But the stars which are formed are of typically lower mass because you cool so efficiently. So the stars are also relatively what we call cooler, which are small mass. The earlier stars are likely to be heavier. Okay, and that is what will probably explain this. Again, as I said, it may not be the whole story. There could be something we are missing still, but yeah, this is something like everyone working with JWST data are thinking about it, and they may or may not agree with each other. This part. Again, this is the part what the data needs to some extent. I won't trust this part a lot because here we are coming to the end of the data. What has happened is we had to put some regularization in the model so that things don't keep on increasing arbitrarily. And probably that regularization is setting in here. So this is probably a model artifact. And as I said, there is no data, so we won't be able to tell you what is going on here. So this part you should not take too seriously. Yeah. And I mean, even if it was serious, at the moment I don't have a way to explain why something will increase up to this point and start decreasing. So that's also, yeah. So as I said, it's too many questions which are unanswered, and data is coming almost on a daily basis. Now this is the galaxy part, and then if you want to model this neutral hydrogen ionization, you have to do a lot. Okay, so you have to first talk about whether these photons will escape from the galaxy. I think I talked a bit about it in response to one of the questions. You have to model the radiative transfer of these photons through the intergalactic medium as it ionizes the universe. And as I said, physics of reionization as a result contains a wide variety of fields in astrophysics. You need cosmology and structure formation. You need galaxy formation and interstellar medium. You need how radiation propagates in the intergalactic medium. And then this is true for all astrophysical observations. I mean, once you have a model, you should be able to predict observables and able to do statistics with those observables. Otherwise, you won't be able to infer the parameters of the model. Now, theoretical model is extremely challenging, and I'm going here very quickly because you need models which have very high dynamic range. This radiative transfer equation is extremely complex to solve. It is a semi-dimensional partial differential equation, and you have to solve in a cosmological setting. So nobody, I mean, even with like far future computing power, we don't think we will be able to solve this in its full glory. And then parameter inference is a different problem because there are so many things which are unknown, as you would have realized from answers to your questions. We have to kind of parameterize those uncertainties, and it is very then you have to run these simulations or whatever model you have by varying those parameters and see which ones the data likes. So if your model is computationally not very efficient, this becomes a very challenging thing to do. So if you run a full-scale numerical simulation, and there are a lot of progress there, they take months to run often. Then you cannot do the parameter space exploration, and vice versa. If you want to do parameter space exploration, your model will be simplistic. Then you may be missing physics. So that is the kind of trade-off you have to do. So there are different approaches to modeling, and we have been working on a set of analytical models, and more recently a set of semi-numerical models. So semi-numerical models is you will actually do a simulation, but you won't actually solve all these equations fully. You will make assumptions and approximations and try to solve them. So they will be fast, but you will get simulations. What I will do is I will skip this part and straight away go to something something more relevant. Okay. So what happens is, if you make analytical models like the model of this luminosity function JW galaxies I showed, they are useful for basically mostly computing globally average quantities. So if you want to calculate the globally average ionization fraction, analytical models are good. But there is more information in the fluctuations in the signal. This is another movie where what I have done is, these are simulations again. I have, in this model, reionization is basically driven by a large number of faint galaxies. Okay. In this case, reionization is driven by a small number of very bright galaxies. They are kind of, how much radiation they are producing is by hand adjusted so that the globally average quantities, like the global reionization history, is exactly same. So at a given redshift, both these models will produce the same globally average ionized or neutral fraction. However, if you look at the actual fluctuations, they are very different. Here you will see a very small number of small bubbles forming and then percolating. Here you will see a very small number of bubbles forming, but they are big because the galaxies have to be, we have to make them very efficient. So you will see all these big bubbles forming, and here you don't have those. There is a small number of large. Yes. This is a galaxy I'm putting by hand. Yeah. N-body is done. N-body is there, and on top of that I'm painting galaxies inside the halos with different models. So you are changing what we call anion in this case, in the reionization terminology. So as I'm saying, the global reionization history is one thing, but there is, if you want to connect that global reionization history or reionization history to the properties of the galaxies, you have to come to this. Okay, you have to study the fluctuations in the signal. The situation is somewhat similar to, for example, CMB maybe 2-3 decades back. The first thing to detect was the black body nature of the CMB. So that is like a globally averaged quantity. But then once the fluctuations were detected, we learnt a lot. I mean, all this concordance model is because of the fluctuations. So the story will be hopefully same here. We will have some idea about the global ionization history reasonably quickly, let's see. But the main story may lie here, and this is where we are spending a lot of time modeling this. So this is one of the models which we have developed to do that. Yes. Get disappeared. See, this is a slice in a three-dimensional box, and what happens is, and this is a reasonably thin slice, what happens is galaxies have peculiar velocities. So if there is a peculiar velocity, it's probably moved away with its sphere away. Okay, so yeah. But in 3D you won't see anything surprising. You will see a slight movement of the bubble. By the way, this velocity of this bubble moving is a detectable signature in CMB, something called kinetic Sunyaev-Zeldovich effect. So that is something we also use, the fact that bubbles are moving with some velocity. Yeah.
So why does it leave this white blobs in this side?
Oh, that I have painted. So white blobs are the places where galaxies and stars will form.
So that should be the same in that side also?
No, here you will see, because here I have said the galaxies are less in number, but they are very bright. So you will see less white spots here. You can't see because there are few only. Okay, I mean if you look very closely, there will be like 3-4 sitting somewhere. Okay, but they are there. There are here some. Yeah, if you have to look very closely. Yes. So in each halo, you have to populate galaxies. Now it depends, if you want to match JWST, you have to put many things there, but if you want to only do reionization, you have to say how many ionizing photons a galaxy is producing. Okay, and then this is the part, you have to do this radiative transfer. Okay, so here semi-numerically what we do is effectively what is called photon counting. Okay, the number of photons produced is equal to number of hydrogen atoms ionized. But that is incorrect because there will be recombinations also. So this is a basic version of the code which is just this. But with recent versions of our code, now we account for recombinations. These recombinations can be extremely inhomogeneous because high density regions will have more recombinations and low density regions will have low recombination. It's an n square process. You have to have two. No, density of the gas basically, because you need the electron and proton to come close for it to get recombined. So it is n times n which comes into the picture. So high density regions then recombine extremely fast, and those things have to go into this picture. Okay, so it depends on now how much physics you want to put. And that is what we have been doing for quite some time, putting more and more physics so that we can compare with more and more observations. Then this thing. So the moment you go to recombinations, then you have to solve for the temperature as well, because recombination rate depends on temperature. The moment you put temperature, then you have to solve for feedback, because temperature will heat up the gas and next generation of galaxies won't form, and so on. So now the model will become more and more and more complicated, and this is where we are approaching. Gas, okay, at large scales the gas will trace the dark matter, and inside the halos anyway you will convert some part of it into stars. You won't. So inside the halos we are not tracing the very details of the gas anyway. We don't need to.
So whether you put a galaxy or not, it's like my naive thinking is that if the overdensity is above a certain thing, then you have a galaxy.
No, so if the overdensity is above something, you have a dark matter halo.
Right.
But suppose I say that the dark matter halo did not cool efficiently enough.
Or the baryonic content in that.
Exactly, could not cool and could not form stars. The baryons will probably follow the dark matter. It will have gas.
Okay.
But somehow it could not form stars, or the moment it formed stars, something happened and it just went away. This, of course, is a very extreme model. I don't think this model is correct. This was just put in to show you visually how different they can be.
So
but in principle, this,
So the baryonic content in a halo is the only variable I can think of.
No, whether they will be able to cool.
But
and
that
fragment.
is all known physics, right? Whether, if you have a certain density.
The essential physics is known, but we haven't solved it in a very fully nonlinear setting. So if I give, like the equation, a very complex gas structure in a halo,
Meaning the fluctuations of...
Exactly, because the gas is not homogeneous. It is extremely patchy. So at what point it will start fragmenting, at what point it will stop, what kind of cooling mechanisms will be important. So all these things have to be done numerically in a simulation.
So the n-body initial condition would be the same for both.
In this case, I have used the same initial condition. Exactly. Yes, just to make the point. Yeah. Yes. And as I said, I mean, there is a lot in fluctuation, and one is hoping to do this using the 21 centimeter signal. So what has been shown here is the evolution of the 21 centimeter power spectrum, which measures the fluctuation as a function of K. So this is scales, but these are small scales and these are large scales. And you can see as the universe kind of, the ionization grows, this power spectrum does extremely funny kind of things. And we understand why it does what. And when the universe completely ionizes, this signal just vanishes. Okay, there is no neutral hydrogen effectively. Okay, so this is what one is trying to detect using 21 centimeter experiments, and the hope is this will tell us about not only how reionization progressed, but what kind of sources reionize the universe, because that will be encapsulated in some of the summary statistics. In principle, yes, but as I said, Lyman alpha gets saturated very quickly, so you can correlate only at end stages of reionization. But end stages of reionization means the neutral hydrogen has been depleted, so the 21 centimeter their signal becomes extremely weak there. So it is non-trivial. What you can do is you can correlate the 21 centimeter signal with the galaxies. They will be completely anti-correlated. And there are predictions from our model, from our model and other models. Wherever you see overabundance of galaxies, you will see less 21 centimeter. And that's a good probe of this picture. No, because we don't have the 21 centimeter signal. We have no detections of the 21 centimeter signal, even in cross correlation. We have detected 21 centimeter signal at low redshifts, not at these redshifts. Yeah.
And there it has come essentially from galaxies.
There it has come essentially from galaxies, so there it is positively correlated, because where you have galaxies, there you have neutral hydrogen, and that the physics is very different. So we are not talking about reionization bubbles anymore. Yeah.
So why it will first decreasing then increasing?
Which one? This one. I will explain to you later. But the idea is, okay, fine. So what is happening is, you initially neutral hydrogen is this are relatively large scales. Neutral hydrogen is roughly following the underlying dark matter, because everything is neutral. So now what is happening is, in high density regions you are forming galaxies and you are ionizing that part. So the regions which had more neutral hydrogen, you are wiping out neutral hydrogen from there. So as a result, you are decreasing the fluctuation. So that is why at some point it starts decreasing. But now the bubbles grow, and again it becomes very rich in structure. So now we will have points where there is neutral hydrogen and points where there are no neutral hydrogen. So now again the signal will start increasing. It will increase and it will be maximum where universe is roughly 50-50, and then it will decrease because you are now wiping out all the neutral hydrogen. So this is the understanding. But the story will be different at a different scale. Okay, that is why I was trying to not answer here. But large scale it is easier to understand. And this 21 centimeter signal is extremely exciting for us, because there are several probes ongoing and planned. So these are probes which are trying to detect the 21 centimeter signal. The MWN LOFAR, Australia and Europe, Netherlands. And GMRT, again GMRT is a telescope which is kind of built and maintained by the institute which I work in. It's some 80 kilometers from Pune. It has all these dishes. This was in fact the first telescope which tried to detect the 21 centimeter fluctuations from reionization, and it put a nice upper limit. Later on all these telescopes came up and kind of overtaken GMRT there. And in the future we are expecting this field to be kind of revolutionized by SK, and I will talk a bit more about SK. But as I said, it is basically the challenge to detect the 21 centimeter power spectrum because it is a weak signal. There is signal from other astrophysics, basically astrophysical sources at the same frequencies. It's extremely difficult to observe this signal. So currently we have upper limits from the present experiments, and these upper limits are becoming kind of improving, becoming lower and lower, and at some point we hope that we will detect the signal, but we are not there yet. And from the theoretical side, we are using all these simulations to make forecasts from what is expected from the SK, accounting for all these challenges, foregrounds and other systematics basically. So the question you can ask is, with all these systematics present, we will be, even if you detect the signal, whether we will be able to understand anything about reionization. So we are trying to answer these questions with making forecasts and things like that. And as I said, we have developed our code script, which is publicly available. And there's a wide variety of people who are basically extending this basic version of the code, accounting for all sorts of extra physics. So as Samir was asking, this is thermal history is something which we have done to account for recombinations and so on. So then 21 centimeter forecast, parameter inference, and so on. And now the code is versatile enough to predict a wide variety of observations like the Lyman alpha absorption. Again, I'm not going into the details. I'm guessing we are like well into beyond the time. We can go and measure the IgM the temperature of the universe and do that. We also have the reionization will also have implications for CMB. In particular, it may affect the B-mode polarization signal, which is the signal from the primordial gravitational waves. It may basically contaminate that signal. For parameter estimation, we have to take help of machine learning now, and that has become inevitable. And this is something we are trying to develop quite a bit. We have developed something called emulators, where you don't need to run the simulation for every parameter. You train it for a fixed set of parameter values, and the machine, whatever, the trained network should be able to predict for all the other parameters. And in the future, we want to see if we can vary cosmological parameters and go into something called simulation-based inference, which have become, again, a very useful handle to do parameter inference, where your model is essentially a simulation, not an analytical model. And I want to spend just 2-3 minutes telling you about SK. So this is basically, we are hoping once the SK comes, it will be able to detect the 21 centimeter signal we are after, and that will basically answer most of the questions which I was trying to probe, trying to basically throw. So it is headquartered in the UK, and there will be kind of a set of dishes which will come up in South Africa and dipoles which will come up in Western Australia. For reionization, this part is what is more relevant, whatever is coming up in Australia. And SK is happening as we speak. I mean, these telescopes are being deployed, so it's not a future telescope. It's being built. It's a multinational project, so it is being basically a wide range of countries are part of it, and covers almost all the continents in the world. It's mostly driven by countries in Europe, but you can see India is also a part of it. So all these blue ones are SK countries. South Africa and Australia. No, this is the headquarters in UK. So these are 3 kind of nodes of SK, and all others are countries who are contributing to the project. And we are one of them. And the timeline, as I said, is very close. So what has been shown here is something called sensitivity. So we want the telescope to be as sensitive as we can make. And these are basically sensitivities of SK as it is being built. You put more and more antenna elements, the sensitivity increases. These dashed horizontal lines are sensitivities of the present day radio telescopes. And you can see, and this is basically the year. So somewhere around 2026, 2027, so we are talking about 1.5 to 2 years from now, SK will become as sensitive as the existing telescopes, and it will be complete somewhere around 2029, 2030, and where it will be like going into the next generation of, it will become a next generation telescopes, and that is where it is expected to give you like new science, which is not possible with the existing telescopes, and epoch of reionization is just one of them. Remember, it is not being built only for epoch of reionization. It is just one science case amongst many tens or hundreds. So it's a very versatile telescope. India has been involved with the SK since the beginning. In fact, Govind Swarup was he proposed one of the first concepts for SK. India contributed to a wide range of packages in the telescope, and it is involved in almost all interesting science projects relevant. And within India, it is coordinated by something called SK India Consortium, and you can see a wide range of organizations and institutions are either part of it or kind of associated with the SK India Consortium, which we call SKIC. And we also have something called science working groups, which coordinate the science activities within India. So if you are interested to know more about them, please let me know. So I will come to the end of my talk with this. So I wanted to basically give you a few take-home messages. So first stars is kind of final frontier of observational cosmology. We are going to try to detect a signal from the phase of the universe where we haven't had any signal so far. JWST and the future extremely large telescopes, they are one of the major science cases is to detect the first galaxies directly. But you have to have complementary studies through, for example, neutral hydrogen. And within this neutral hydrogen, we already have quite a bit of observations, but one expects this 21 centimeter fluctuations to kind of open a new window. We already have interesting limits from the existing telescopes, but we have to look forward to the SK for actually the detection of the signal. And on the theoretical side, we have made good progress in theoretical modeling, but we still need to do a lot to interpret the SK data, because these data sets are going to be extremely rich. So I will stop here, and thank you very much.
Thank you, Professor Rai Chaudhuri, for this brilliant overview, and thanks. I would like to thank the audience also for so many interesting questions. So we can have a few more questions if the audience have a few.
I'm around. I don't have.
Okay.
Lyman alpha usually gives a bound on the dark matter mass, like it has to be greater than a few keV. So does 21 centimeter also give something similar?
Remember, 21 centimeter we don't have a detection yet. So we cannot give a bound, so to speak, because we haven't detected the signal. We did some analytical calculations to forecast what will happen with 21 centimeter studies.
Okay.
And this is the kind of forecasts we get. So, since we are making forecasts, we have to assume what could be the dark matter model. If it is CDM, you will get something like a bound of 8 keV when the 21 centimeter studies become available. If, for example, it is indeed a 7 keV, let us say, dark matter, we will be able to probably detect it, okay, using 21 centimeters. So these are the kind of, so this is the best we can do in the absence of a detection of a signal. So yes, we are making forecasts.
And at the end you mentioned it can probe the nature of dark matter. So
Yes.
how does the nature...
Okay. This is one way. You suppose you say that it is basically a thermal relic. You can try to measure the mass of the dark matter particle up to this level, because beyond 7 or 8 keV, these models become indistinguishable from CDM at the scales we are interested in. Okay. Of course, what we are essentially probing here is the fact that power gets suppressed when the dark matter is relatively light. So what we can do is, you can go and say that I don't care about the model of dark matter, whether it is thermal relic or warm or whatever. I want to measure the suppression in the power spectrum. Okay, so that indirectly will tell you about the nature of dark matter, but maybe not uniquely. There could be many models of dark matter which give you same kind of suppression, but this is what in principle cosmological observations will be able to give you limits on. So that is what I wanted to highlight. Yes. No. So if the actual mass is 7 keV, 21, when you compare with the data, it will tell you that this is the 95% confidence level, but it is between 5 and 10. So it will be like 7 plus minus something, right? What did I do? Okay. Yeah. Sure. So this is the green curve. Yes. Thanks for catching that. Yes.
So the quasar that you talked about, what are those? Are those galaxies like any other, or are they special galaxies?
These are special galaxies. They are something called active galactic nuclei. So our understanding is, which is reasonably well understood, is that you have the central supermassive black hole, and that is basically accreting matter and eventually giving rise to radiation from there. So for cosmological purposes, for the kind of studies, we really don't need to understand what these sources are. They are like background torchlight. So some torchlight is being shined, and whatever is in intervening, we are trying to understand that. What we need is a very bright source, otherwise we won't have enough signal to noise to capture all these absorptions. So in principle, one could do this experiment with normal galaxies also. But normal galaxies, the flux level will probably be somewhere here and you won't be able to see them. With next generation of extremely large telescopes, those are being built, people are planning to do Lyman alpha forest using galaxies. So then there will be Lyman alpha forest in every direction, and it's a completely different field then. But you have to wait for some.
So if you take one of these, like this one, in an observation like that,
yes.
Is that a known quasar that is...
Yes. Yeah, you are looking along a known quasar, integrating for some time, few minutes to few hours, and getting this spectra.
So what is the largest redshift quasar we have?
The 7 point something. Okay, that is where we are currently.
And every Lyman alpha forest observation is to do with some quasar that we know. Is that...
Yes, Lyman alpha forest is always along a known quasar. What will happen is at redshift 7 quasar, this part which we are interested in, it will be completely kind of blank. You will only see noise. Yeah, so that is where we are. But that doesn't mean we cannot infer anything about neutral hydrogen there, because there is something called damping wing, Lorentzian wings and things like that. So there's still information, but you have to go and model that. Good, yeah. So we already we have seen quasars. Now that is, in fact JWST is not seeing quasars, but some remnants of like black holes at high redshifts, and there are many of them. So it's not related to what I talked about, but all these things are bringing up newer and newer questions. Because to form that central supermassive black hole, you need to give the universe some time. It's not clear whether there was enough time to form those black holes at the redshift they are being observed. Boost these, yeah. So I have to appeal to something non-standard. Yes, in principle, yes. So these are being talked about now, but yeah.
So can I ask a question? There was this plot of delta H1 as a function of redshift you had.
Delta H1.
21 centimeter, yes. There, this one, as a function of redshift.
Yeah, so this is a power spectrum, KQP of K.
That is correct, the bottom one.
Yeah.
Now, will there be any correlation with if you do the same thing for just dark matter?
For dark matter, okay, these are reasonably linear scales, so
that's what I was wondering, whether, something is scaled because it is constant for a long time.
Yes, so here it is actually dark matter, basically. Essentially it is dark matter.
That's what I want.
And this is where it is deviating
I
from
understand.
underlying dark matter and doing all these things.
Because it's well inside the Hubble radius. I mean, on those.
Oh yeah, but linear also. So this
Okay.
is reasonably, you can, so this part it is
Is-
probably d square z times.
Yeah, I understand.
Yeah,
That's what I
yeah.
want. Thank you.
Observation, sir. These low intensity galaxies are more in number in the observation. Is it the selection bias or it is the
No. Selection effects are taken into account. Which these ones, right?
low flux galaxies are more in number
Yeah,
compared to
faint. It is something like this.
yeah.
Yes. So, so there is no observational effect. You really have more observed more faint galaxies than brighter ones.
So
There is,
it exists actually.
it is real. It is real. No doubt about that. And that is not difficult to explain also. So, for example, dark matter halos, if you plot the halo mass function, you will have more small mass halos compared to, but that doesn't mean the scaling is simple. It's not like you just populate every dark matter halo with some galaxies with some luminosity, which is a simple function of halo mass. That it is not guaranteed that they will produce this one. Okay, so there the astrophysics becomes important, but the fact that faint galaxies are more is not, it's across all redshifts, except at low redshifts, we have seen where it turns over, because we believe we have seen all the galaxy population. At high redshifts, we don't know. So where is this limit? Okay, minus 17, minus 15, minus 12, observationally we don't know. Theoretically, you will have a limit. It will come from your theoretical model. Because very low mass galaxies won't be able to cool. Low mass halos won't be able to cool. So it will. Yes.
Baryons in the halos. So
Yes.
So if we have bigger halos, they have higher virial temperature and they will start at a higher temperature.
Yes.
And so initially they have some cooling, but then again they will come to a temperature of the lower mass halos.
No, okay. Yeah. So what will happen is, it is slightly non-trivial. The moment you cool, you will also condense. Okay, so the phase space changes basically. So density is increasing, and then this is basically roughly a Jeans mass argument. What will happen is the Jeans mass will decrease because they have decreased the temperature. So things will start fragmenting. Okay, and then this can become a runaway process basically. So yeah, it won't come to equilibrium very soon, but it has to come to equilibrium. Otherwise you will keep on fragmenting and it will form like Earth mass stars. Yeah. So there something to do with the optical depth changing. It becomes so dense that this radiation which was coming out and helping cooling, that cannot happen anymore. The radiation gets trapped inside. And you can show by order of magnitude calculation. So this is what Martin Rees, Silk and all would have shown. Order of magnitude calculations show that for typical cooling rates and other things, this number comes out to be 1 solar mass. So they explained that, okay, stars have to be 1 solar mass. Yeah. But this is the rough argument. Of course, this is a very simplistic argument, but what actually happens is maybe much more complicated than this.
So fainter means less massive, or is that not?
Yeah, most likely, yes. Well, because mass to light ratio, the way we see in our in our local universe, yes, lower mass galaxies are fainter. It may not be exactly 1-to-1 or exactly linear, but roughly yes. But at some point this will turn over. So at that point what will happen is we will have the dark matter halos sitting, but it is hosting either very faint galaxies or no galaxies. No, that cooling. Baryons are also probably sitting, but they are not producing stars. Okay, so gas is there, but luminosity, light is not there. They are not producing light. So that cooling argument becomes important. So you are asking something? No, these are intrinsic luminosity. Yes, so this is absolute in that sense. Yeah. So that faintness is already accounted for. Yeah, this is corrected for. Yeah.
Since there are no other questions, let's thank Professor.
Thank you very much.
And he is here for another 2 days in the office 303. So if you want to talk to him, discuss physics, I have sent an email to his group. You can send an email to teach@ncr, the one that I sent.
You can just drop in. I am not.
Okay, but you can set up a time, or you can just drop in, as he said. Okay, there is some arrangements of tea and coffee and some snacks outside, so we can go and have them now.